Hi, this is Daryl Osborne, and I'm a solutions architect with Amazon FSx. In this webinar, I'm going to give you an introduction to Amazon FSx for Lustre. So during today's session, we're going to talk a little bit about, what does it take to run compute-intensive workloads on AWS and what that means. We'll also go into what Amazon FSx for Lustre is, a new storage platform that we relaunched at reInvent 2018. Then we'll see FSx for Lustre in action. We'll do a demo of how you're able to achieve high levels of throughput and actually create a file system and get high levels of throughput from your file system. We'll do a quick summary at the end, and then we'll have some Q&A. So what does it mean when I say running compute-intensive workloads on AWS? So, any workload that really processes data at a rapid pace with lots of compute power. Or really another way to say that is a workload that processes large amounts of data with large amounts of compute. So typically massive data sets and large clusters of compute are involved in these workloads. And commonly they require fast storage with high-speed networks between the storage component as well as the compute component. And in AWS, we have a number of different services that supports this these compute-intensive workloads. So we have Amazon EC2 instances. So we have some that are really designed for these HPC workloads. EC2 Spot is a great way to launch and run, scale out and run massive amounts of compute at a very cost-effective price, and then tear down that compute cluster when you don't need it. We also have auto scaling, so you automatically scale your cluster out, run your processing, your jobs, and then go ahead and scale that back down. In terms of automation and orchestration, we have a number of services here as well. So we have AWS Batch, CFN Cluster or Parallel Cluster. We also have Amazon SageMaker. So again, all of these are geared towards these HPC type workloads, these compute-intensive workloads. On the networking side, we have enhanced networking. We have placement groups that will allow you to achieve high throughput between your cluster nodes. And then we have a number of visualization services like NICE and AppStream 2.0. At reInvent 2018 this year, we also released a number of other components that are geared towards HPC workloads. So one of them is elastic fabric adapters, or an EFA, as well as a new compute instance family, the C5N, which is really designed to have up to 100 gigabits per second of network bandwidth. Again, all of these services and components are geared towards these HPC or these compute-intensive workloads. So, once you have a workload that is that you're going to be running in AWS, typically you store your data set in S3. And S3, this is your long-term, durable, low-cost data store. And typically you would have two ways to get this data into a compute environment for your application to run. One option is to copy that data to an EC2 instance. This could be instance store, or it could be EBS volumes, but you would copy it from your S3 bucket onto these compute instances themselves. The second option is to copy the data into a self-managed high-performance shared file system. And again, there's a number of different options available there, but this is typically customers would use either option 1 or option 2 in order to get their data onto a platform that is accessible to their application to run these compute-intensive jobs. Once your jobs are complete, this processing is complete, typically you have results that you want to write back. So you would then write those back to S3 so you can do some analytics on it, and you can at least save that data off for another time. So both of these options really expose the data to these compute instances via a file system. And it is, so why file systems in this case? So in terms of latency, file systems offer you great latency, low latency to your data, which is very important for these types of workloads. In terms of request cost, with the file systems, you don't have request cost. But with Amazon S3, it's really not designed for these types of workloads where you're accessing the same data from multiple instances in parallel. So you're going to have a number of very high amounts of request costs with a workload like this. And a lot of these applications require a file interface. And you're just unable to get that from Amazon S3 because Amazon S3 is object storage. So, some of the requirements to have a shared file system is really this POSIX interface. It really allows these applications to get access to this data using a hierarchy or a directory structure, and they're able to access and work with this data like it would be local storage. And most operating systems, they natively work with file systems, so it's a very good fit for these compute-intensive workloads. Also with the shared file system, you're able to achieve high levels of throughput in IOPS, able to serve this out to multiple compute clusters, and really be able to provide near local latencies for your data. So most compute-intensive workloads that use shared file storage use what we call a parallel file system. And with traditional file systems, you have a single file server that all clients speak to. But with a parallel file system, it really avoids some of the typical bottlenecks you would have in this typical client-server architecture. So clients interface directly with the servers hosting the data set. So with a parallel file system, the data resides on individual storage servers, and clients can access the storage server itself to get access to the data, and it doesn't have to go through basically a single point to get access to it. And most of these storage servers have multiple disks, and the data is striped across them, so you're able to achieve high levels of throughput and operations per second as you access this data in parallel. But one of the challenges with parallel file systems is that it's really hard to run. Typically, it requires highly specialized expertise. A lot of the customers that we spoke with actually have full-time engineers that their primary responsibility is to manage these parallel file systems. So it is a very difficult challenge. It's difficult to configure and maintain the software stack to support these clusters, and there's a large number of parameters that need to be set in order to get the best performance. So it really does take a lot of effort in order to support and maintain these parallel file systems, and it's really difficult to keep it alive all the time. So because of this, we typically see it's out of reach for a large number of organizations unless you're really lucky enough to have the experts managing it in-house. Most of these environments are multiple petabytes in size because they're really built for peak capacity so that multiple teams can have access to the server. So this really means that you would have tens or hundreds of servers, hundreds or thousands of disks behind them. And again, this is one of the challenges in keeping a parallel file system alive, is that it would require a team in order to maintain all of these servers and all of these disks. Another challenge is moving massive amounts of data into and out of a parallel file system. It is as you're trying to access this data, you need to import it in from your data repository. Typically, you would have to write scripts. You would spin up an entire fleet of EC2 instances, and again, access your data in S3 in parallel and write it to your file system. There's a lot of work involved in trying to do that. Then at the end, again, you're going to have to take that data that you want to persist beyond your batch job, and you want to persist that back to Amazon S3. So again, you have to write something to that. So there is definitely an art, and it is a challenge in order to move massive amounts of data into and out of these compute clusters. Well, we received a lot of feedback from customers, and this is something that we wanted to do better. We wanted to help customers have a better experience when working with these parallel file systems. And that's one of the reasons why we built Amazon FSx for Lustre. So Amazon FSx for Lustre is a fully managed high-performance parallel file system on AWS. So it really makes it easy to run a high-performance Lustre file system that's really accessible for all of our customers. It is seamlessly integrated with your existing data repositories in Amazon S3. And as you see a little later in the webinar, very easy to launch and get up and running. Some of you may be familiar with Lustre, and some of you, this may be a sort of a new file system. So Lustre is one of the most popular file systems, parallel file systems out there. It is open source. It's been around for over 15 years. I think it was back in 1999 at Carnegie Mellon. It was started as a research project, and it has really matured into a file systems that is used by businesses, research institutions, and the government. And there's a wide variety of use cases. Actually, in fact, over 60% of the top 100 fastest supercomputers leverage Lustre file systems for data storage. As I mentioned, there's a wide array of different use cases, anywhere from seismic processing to geospatial, financial modeling. It's very big in the media and entertainment industry, and even EDA workloads leverage parallel file systems like Lustre. So some of the key benefits of Amazon FSx for Lustre is it really allows you to have massively scalable performance for your file system. So it is a linear performance model. So as you provision larger file systems, linearly you'll be able to achieve even more and more throughput to your file system. It is seamlessly integrated with Amazon S3, so you have access to your existing data repositories. So again, a very easy process to move data into your file system from S3, and then any data that you want to persist and write back to Amazon S3, it's very easy to do that as well. It is very simple and easy to manage the file system, and again, I'll show you a demo when we create a file system here a little later. You have native file system interface with Lustre. This is a common file system in the compute-intensive workload sort of arena, and so many people are familiar with just how it works, how it behaves. It's going to behave and work like just any other file system that a Linux operating system is able to use. It is cost optimized for these compute-intensive workloads. So that's one of the core tenets when we built the service, is that we wanted to make sure that it was cost optimized and allow great performance to this file system. And it's also secure and compliant. And we'll talk a little bit more about that later in the session. So when I mentioned massively scalable performance, again, because this is a parallel file system, you're able to achieve high levels of throughput. So how high? Really tens and hundreds of gigabytes per second throughput. You're also able to achieve hundreds of thousands and millions of IOPS. and have consistent sub-millisecond latencies to your data. Your data is stored on SSD storage, so it allows you to get this level of performance and throughput and operations and latency that I mentioned. It also supports hundreds of thousands of cores. You're able to get, thousands and tens of thousands of clients accessing your file system in parallel. So in terms of performance, as I mentioned, with each terabyte of data, it literally scales. So with each terabyte of data, or each terabyte of storage, it provides you 200 megabytes per second throughput for your file system. So as you create larger and larger file systems, it's able to linearly scale the throughput up. And again, you're able to achieve millions of operations per second as you have larger and larger file systems. So it is seamlessly integrated with S3. So when you create a file system, you can optionally link it with an Amazon S3 bucket or a prefix within a bucket. Then your data is loaded into the file system by issuing a couple of commands. Once that data is in the file system, you're able to process it, get access to it from your clients, do that processing. Once that processing is done, you can go ahead and commit that data that you wrote back to Amazon S3 for later analysis. Once you're done with that, typically you would tear down your compute cluster and tear down your file system. So when a file system is created, we load the file name and the directory structure of those files into the file system. So you can do a simple ls against your file system, and you can see all the objects that were in that bucket or that bucket prefix are now available in your file system. The data is not there, but the file name and the directory structure is. So this is what a lazy load process would look like. When you first call that file, if the file system is not, if the file is not in your file system, it would go ahead and retrieve and get that file, that object from S3, load it into the file system, and then deliver it to the client. So in this example, we have file 1. The client access or requests it from Amazon FSx for Lustre. The data doesn't reside in Lustre. So what it does, it actually goes out to S3. It grabs that object, gets it, puts it into the file system, and then returns that back to the client. Subsequent reads either from that client or from other clients, when they try to access that file, no longer does it have to go back to S3 because the file data resides in the file system, and now it's able to go ahead and return that file in sub-millisecond latencies back to that client, so you're able to get a very fast, high throughput, high IOPS access to that data. So each FSx for Lustre file system is built on a cluster of file servers. And each of these file servers will have one or more disks. So data movement to and from your linked S3 bucket is done parallel across all of the file servers hosting the file system. We do use multi-part uploads and downloads to move large files quickly to and from your S3 bucket. So a lot of folks really wanted to burst into the cloud, meaning that they want to spin up these large compute clusters in AWS and run these large compute-heavy jobs. Then when they're done, go ahead and spin down that compute when you don't need it. So there's a lot of scenarios where you have data on-prem that you need it in AWS while the job is running, so that the compute cluster will have local access to that data. So again, you can go ahead and mount your file system from a computers on-prem over a direct connect or a VPN connection. And then you go ahead and move that data from your on-prem data store over to your Lustre file system. So earlier I mentioned that Amazon FSx for Lustre is simple and fully managed. So what that means is we provision and set up all the file servers and the storage volumes for you. And that's just a part of the file system creation process. As a part of that process, we also configure and maintain that Lustre software. So no longer do you have to maintain the hardware and the software behind your Lustre file system. And we also give you very easy tools to manage the movement of data in and out of your Amazon S3 bucket. It is POSIX compliant, so your applications can work with files and directories just like they do with a local file system. So included as a part of this is that we do support read after write and read after close consistencies. Which is super important as you'll commonly have multiple compute instances accessing the same file. So you need to provide these consistency guarantees. It's also important for workloads that have lots of compute instances accessing the same files. So we support file locking as well. It is secure and compliant. So your data is encrypted at rest, and we support PCI DSS and ISO compliance, and we are HIPAA eligible, and all of this day one of the service. You can control network traffic to your file system using standard Amazon VPC security groups. Again, you can have 1 to 5 security groups associated with your file system. Admin API access control is controlled using AWS IAM, or Identity and Access Management, and all of those admin API calls are monitored and logged using AWS CloudTrail. Amazon FSx for Lustre is cost effective. It is really cost optimized for short-term compute-intensive workloads, providing non-replicated data or non-replicated storage. So it is designed to work with your long-term storage, durable storage on S3, and that is typically where your long-term data would reside. And then you serve that storage up to your file system when you need to, so you can process it. You can spin up and down these file systems as needed. The long-term data is stored in S3, and then or either on-prem or in S3, and then when you need to process it, you would basically an on-demand file system, you would spin it up, load in the data that you need, process it, and then tear it back down. The price of the high-performance SSD file system like Amazon FSx for Lustre is, we've priced it at 14 cents per gigabyte month. When talking to a lot of our HPC customers, they really think of storage in terms of, and processing in terms of hours, because typically these jobs or processes will run for hours, maybe days. So that actually equates down to 20 cents per terabyte hour. So you can sort of do the math and see, how much will it cost to run a particular process or a job if it's going to run X number of hours. So let's just walk through a TCO example. And in this example, we have 250 terabytes of data. This 250 terabytes of data resides in an S3 bucket. And you want to run these daily processes, and you want to process the last month's worth of data. So these processes typically are, in this example, are 25 terabytes of data. You require 5 gigabytes per second throughput, and they run for 10 hours each day. So if we go ahead and do the math, that would equate out to $1,500 per month for your Amazon FSx for Lustre file system. That's really for the storage during the compute or these processing runs. Your long-term storage of 250 terabytes resides in S3. So in this example, you'd have $5,700 per month of S3 storage for your 250 terabytes of data. When you move that data into Amazon FSx for Lustre and process it there, that would be an additional $1,500 per month. And in this example, it would cost you $7,200 per month in order to run this type of workload, and that equates out to 2.8 cents per gigabyte month for this workload. So again, you can see that it is very cost effective when you have your long-term storage residing in Amazon S3, and then you move in just the data that you need to process into Amazon FSx for Lustre, and then go ahead and tear that down. So we have a lot of customers in different industries and that have different use cases interested in Amazon FSx for Lustre. So it really is designed for HPC type workloads. So high performance computing is great for Amazon FSx for Lustre. Machine learning is also a great use case. Media and entertainment, so media rendering and transcoding, where they need high levels of throughput. Data analytics, EDA or electronic data or design automation is a very important use case. Financial modeling, oil and gas, seismic processing, and even autonomous system training. All of these are great use cases for parallel file systems like Amazon FSx for Lustre. It is available today in these 4 regions: U.S. West Oregon, U.S. East Northern Virginia, and U.S. East Ohio, as well as EU Ireland. And we have many more regions coming online soon. So with that said, let's go ahead and see FSx for Lustre in action. Really the best way to share more about how we've made Lustre file systems, accessible and easy, seamlessly integrated with existing data repositories that reside in Amazon S3, and easy to launch and run is really to see it in action. So what I'm going to do is go over to the FSx console, and we're going to create a new file system. So from the console, I just click on Create File System. Here I have the option to select one of 2 file system types. So again, in this example, we're going to select Amazon FSx for Lustre. Scroll down and click Next. Here we would give it a file system name. This name isn't used to access the file system. This is more of a key value pair. So I'll just go ahead and call it file system A. Next, we put in the storage capacity. So this can be anywhere from roughly 3 terabytes all the way up to, we have a soft limit of 25 terabytes. So in this example, I'll just go ahead and put in 3,600 gigabytes. When I tab off, it does give me based on the amount of storage capacity that I selected, it does give me the throughput capacity. Again, this is based on 200 megabytes per second per terabyte of storage capacity that I provision. As I scroll down, we do give you an estimated monthly cost based on the size of your file system. We would also select in the network and security section where this file system is going to reside. So we would select the VPC, the virtual private cloud, where it's going to live in. We'll go ahead and select the default VPC. We can select any one of the availability zones that are available. In the subnet, if I have multiple subnets, we would select a single subnet where my file system will reside. And then I can associate 1 to 5 different security groups with my file system to control network traffic to my file system. If you want to optionally link it to an Amazon S3 bucket, you can go ahead and do that here and supply the bucket name or the prefix to data within that bucket. In this example, I'm not going to select anything. And also you have a weekly maintenance window where if maintenance is required on your file system, it would be started within this 30-minute window, and you could optionally select the day, hour, and minute when this 30-minute window is going to start. I don't have any preference on that, so I'm just going to go ahead and click on Next. We can review the settings from the previous page and click on Create File System. So it really is that simple and easy to get up and running. So what, in a previous example, in previous test, I created a file system and I linked it with an S3 bucket. The bucket that I linked it with was the NASA NEX. It's an open data source bucket. The NASA NEX is a platform for scientific collaboration and knowledge sharing. It is there's a number of different types of files in this bucket, anywhere from net CDF files, which is the network common data format. It's really used for storing multidimensional data files. There's some TIFF files in there. There's also some HDF files, some hierarchical data format files, which are designed to store and organize large amounts of data. There's PDF and text files, MB5 files, a number of different files within this bucket. So during my previous run, when I actually created this video, I linked my file system to this bucket. And during the creation process, what happens is that the object names and the prefix of those objects are copied into the file system, and the file names and the directory structure is created. And in this example, we were able to move in 373,000 objects, at least the file names of those objects and the directory structures of those objects, in roughly 11 minutes. So we were getting a creation of around 567 objects per second, moving in the object name and the directory structure, the prefix of that object. So again, this is the type of data that I'm working with. .nc files, or these net CDF files, TIFFs, HDFs, around 373,000 different objects are associated with, are in this bucket that I'm going to be working with today. So in a lazy load example, what this is really the ability to move in the data of individual files when you need to access that file. So let's go ahead and jump over to my SSH window. So at the top window, I actually just have nload running. Both of these windows are open or have an SSH session to the same EC2 instance. And down below, I'm going to go ahead and run some of my commands. So if we do a simple mount for Lustre, just to see what Lustre file system is created, we do have a Lustre file system mounted to this EC2 instance. If we issue a LFS command to do a DF of that file system, we can see that we have a number of different OSTs, or object storage targets. So again, all of this is created as a part of the file system creation process. We have an MDT that stores all the metadata for your file system, and we have individual OSTs created based on the size of your file system. Each one of these, as we can see here, being 1.1 terabytes in size. So because I linked this to an Amazon S3 bucket, all of the file name and hierarchy or directory structure of those objects were moved into the file system. So we see that's using roughly 4.4 gigabytes of data. And this is all of that metadata, the file structure, the file names of all of those objects in that bucket. But as we scroll down here, we see that we really don't have data within the OSTs, or the object storage targets. So what we want to do is we want to go ahead and take a look at a piece of data, and we want to go ahead and load that in. So let's hop back to a script, and I've got a file here. I'm going to do a simple ls to that file, and we see that this file, it's a TIFF file, it's 181 megabytes in size. So what we want to do is I want to go ahead and simulate an application reading this file for the first time. So I'm simply going to issue a cat command and read this file from what we call the file system into temp fs. So we're just going to be putting it into memory. So as I issue this command, we'll notice that it's taken a few seconds for it to run. And if you saw up above end load, just at the very end, maybe the half a second at the end, we saw some network activity. So why did it take 4.2 seconds in order to read this file, even though we only saw maybe a half a second of network activity of this instance? So what happened was, because the file data wasn't in the file system, when my application, when my cat command requested the data, FSX for Lustre would go out to the linked file, to the linked S3 bucket, grab that object, copy it into the file system, and then return it back. So the only data movement you saw was from the file system to the client. If we issue a subsequent read, or a subsequent cat command in this example, we're able to get that data back very quickly. So again, 0.114 seconds. So some of you may be thinking, well, we didn't see any network activity, and you're right. This data now is cached on this instance. So what do we want to do? We want to go ahead and drop our cache so that we can read it again. And this time, because the data is actually moved into the file system, the next time we access this file, we're actually going to be reading it directly from the file system. So let's go ahead and issue a drop cache command. And now we're going to run our read, or our cat command. So again, as we read this, we're going to see that we just saw a little network activity up here in end load, but it took us 0.467 seconds to go ahead and read in a 181 meg file from our file system. No longer did it have to go back out to Amazon S3 in order to retrieve that data, because the data already resides in the file system. So how do we know that? If we actually go back and do another LFS df-h, we can see that this 181 meg file now is being stored on OST 10. That's where that data resides. So we can easily drop or release that file to remove the file data from our file system. And by issuing this release command, we can do another df, and we'll see that, well, the data is still there. If we do another df, now that data is no longer there. So we flushed or released that file from our file system, but the metadata, the file name and the directory structure is still here. So we're still able to go ahead and issue an ls against that file. And we can still see that it's a 181 meg file. If we do another cat or a read of that file, what's going to happen? Again, it's going to take us a few seconds. We notice no network activity up above. Only at the end are we going to see a little network activity as it's read from S3 into the file system, and then we'll see network activity on our instance from the file system over to the client, or to our instance. So just again, this is another example. We had a 181 meg file. First time we read that file, we had to load that data, that file data from S3. And the example that I did a little earlier was 4.293 seconds. A subsequent read came from the cache, so it was very quick. In this example, 0.109 seconds. But what we wanted to do was flush cache, read it again, and this time it's going to be coming directly from the file system. And in this example, it was 0.396 seconds. Applications, you really don't have to do anything special when working with the Lustre file system. Just realize that upon first access of that file, if that file doesn't already reside in the file system, the data, it's going to have to go out to the S3 bucket, grab that object, move it into the file system first. So you're going to have really first access latency to that file data, and as long as your application can sustain that, you don't have to make any modifications to your application. Now, in some applications, you may want to load some of your data first before running it because it's latency sensitive. So one way to do that is to do a batch load of the objects that you want into your file system. So a simple command like this, where I'm taking all of the all of the files in my file system, and I'm actually issuing a restore command to Amazon FSx for Lustre. And with this command in parallel, I'm able to go out, grab all of the objects from the S3 bucket and move all of those objects into the file system in parallel, achieving high levels of performance. Again, once I issue this command, the client is done. It no longer has to do anything. The data is actually moved directly from S3 into those OSTs, or the object storage targets, in parallel, and the client is not involved in transferring this data. All it has to do is issue the command. So this is really what it would look like. You would have a number of parallel threads getting objects from S3 and writing it in parallel across all of our OSTs associated with our file system. So in my earlier example, I already have my file system created. All of the file names and the directory structure data has been loaded into my file system. You can see that here with this spike in the bottom portion of the graph. Now I'm going to go ahead and issue the batch command to batch load all of the objects. So here, as you can see, the spike, dwarfs the amount of operations per second that was done during the load of the file names and the directory structure. So in this example, we loaded 373,000 objects. In total, it was 22.7 terabytes. It only took us 32 minutes to do this, and we were hitting peaks of 15.8 gigabytes a second. We were also hitting peaks in the operations per second of 528,000. So really able to ingest a lot of data very quickly from Amazon S3 into our FSx for Lustre file system. And again, this was done by a simple command. There wasn't a whole compute cluster needed to ingest this in parallel. It was a very simple command that basically told Amazon FSx to go out, grab all these objects, and copy it into the file system. So you may have a workload that you need to write a lot of data to your file system. So Amazon FSx for Lustre is also ideal for this. You're able to achieve high levels of throughput when you're writing or reading data from your file system, just because of the parallel nature and design of the file system. So in this example, I have a number of different EC2 instances that are going to be writing in parallel to the file system in order to generate a large amount of data. So in this example, we had, I think we were generating about 6.4 terabytes of data, and it only took us around 4.5 minutes to complete. And as you can see here, we were able to achieve high levels of throughput writing to the file system. Based on the size of the file system, I should have been getting 23.12 gigabytes per second. I actually achieved 23.9 gigabytes a second. So again, able to achieve high levels of throughput. This was done just using 20 C5 2 extra large instances, mounting the file system and writing in parallel to the file system. And at this speed, at 23.9 gigabytes a second, you're able to say you wanted to write a 4K movie, which typically are, they're around 100 gigabytes. It would just take you 4 seconds, just a little over 4 seconds to go ahead and write a typical 4K movie to Amazon FSx for Lustre file system. So again, in summary, Amazon FSx for Lustre is a fully managed Lustre file system. It's really designed for these compute-intensive workloads. It offers massively scalable performance. We're able to achieve 200 megabytes per second per terabyte of storage capacity that you provision. It's seamlessly integrated with Amazon S3 so that you can gain access to your existing data repositories. Again, very simple and easy to get up and running, and it's a fully managed fully managed file system. It is a native file system. So your Linux operating systems are going to be able to interact with it because it is POSIX compliant, just like any other file system that that they're used to. It is cost optimized for compute intensive workloads. So we really wanted to focus in on this when we were designing it so that customers would be able to store their long-term data in S3 and then just spin up an Amazon FSx for Lustre file system on demand, run these processes, these jobs, and then to go ahead and tear it down when they're done. And it is secure and compliant day one. We have a number of resources out there, so we do recommend that you go to our FSx Lustre site. We have some videos, some blogs, some white papers, even some reference architectures, and our documentation is great. If you go out to our user guide for FSx for Lustre, you're going to be able to see the commands that I issued today during our demo to do lazy loading files as well as doing a batch load of files from or objects from Amazon S3 into your FSx for Lustre file system. With that said, let's go ahead and have some questions and answers.